Actually sat and I did my lab before. The whole night. That's what I'm worried on this. No, I literally.
Okay.
Yo, mama. Hey, here's. Oh, no. You can't look in China. You have no, I'm not the authority over.
All right, how are you all doing? Did you have a good break?
I'm on break, so. Yeah, it's.
Yeah.
I have break brains.
Okay. Well, I just heard some of you saying, oh, it's the last full week. Can you believe that? You don't want to believe that. Okay.
That's.
But it is. All right, this is acting up. Okay, well, good to have you all. Let's try to remember a little bit fat characterization. The good thing is you did the lab on Wednesday, so you should be able to remember a few things. And then we can finish up this lecture really quick and then get started with pH and titratable acidity, which is the topic of your last lab this Wednesday. And next Wednesday, next week, remember, it's review session. So please do come to the review session. It's important. A lot of the questions that I will be reviewing with you will be on the final. So it's good for you to be there. All right. Okay. So let's do recap. So what are a few physical tests that you could remember that we talked about? Huh? Physical tests. Reactive index, yes, it's an identification. What else? I told you a story about. Smoke point, flash point, fire point. Yep. So these are a few of physical tests that are done for identification purposes, but also to determine the impact of processing. For example, using the oil, frying in the same oil multiple times, creating free fatty acids. Free fatty acids will have lower smoke point, for instance. Yep. Testing winterization by cloud point or cold point. So these kind of tests. Okay. So what is saponification value used for? Do you remember? What did we use it for? Try to shake, vacation, break out, huh? Triglyceride molecular weight, yes. So it's an identification test, and we use it to estimate the triglyceride molecular weight and also the molecular weight of the most abundant most abundant type of fatty acid in that triglyceride in this particular fat. So let's think about this. If oil A has higher saponification value than B, which one has a lower molecular weight of their free fat, of their fatty acid? Huh? B will have lower. It's an opposite relationship. Okay. So A will have a lower molecular weight. Think about it as the larger the molecular weight, you will have less number of moles per 1 gram because it's larger molecular weight. So there is a relationship between the weight, the molecular weight, and the number of moles. The larger the molecular weight, you'll have less number of moles per gram of fat. Therefore, less moles per gram of fat, you have less amount of KOH that is needed to saponify this oil. So it's an inverse relationship. Okay. Which test is used when testing efficiency of hydrogenation? Iodine value. It is used to determine the degree of unsaturation. So if we hydrogenate the oil, fully hydrogenated oil will have an iodine value of 0. So if we have a high percent of free fatty acid, what is that indication of? Potentially. Free fatty acid is part of a hydrolytic rancidity. Yeah. So if we have hydrolytic rancidity due to presence of enzymes, you will have higher free fatty acid. But what about frying oil? The more you fry in the same oil, the higher or the lower free fatty acids? The higher. So think about it's like you're frying potatoes. There's a lot of moisture. Heat, moisture, and then triglycerides will break into free fatty acid and glycerol. So you will have higher free fatty acid in oil that has been used multiple times for frying. Okay, what else did you remember talking about refining? What you did the lab. So did refined olive oil have more free fatty acid, or did the virgin olive oil have more free fatty acid? You remember? The virgin, because refining takes away free fatty acid. Usually you treat with NaOH, you generate soap, you centrifuge, you get those free fatty acids in the soap out, and then you have the oil with low to no free fatty acid. What about peroxide value? What does it measure? What is it a measure of? What stage? Primary. Okay. So it's peroxides are primary lipid oxidation products. If you have a peroxide value of 0, what does it mean? Is the oil fresh? Is the oil fresh? Fresh or really rancid? Because either it's really fresh, so no peroxide have been generated yet, or all peroxides that were generated were converted to secondary metabolites. So it might either smell so bad or it would be really fresh oil. Okay, very good. So let's move on. I appreciate everybody coming in the cold to be here in class. So thank you. Okay, measuring the present state. So we are still talking about measuring the present state. Peroxide value is actually you're measuring the present state when you take the oil off of shelf and you measure the peroxide value, that's measuring the present state. So also there is a test that called the Totox value. It's a combination of two measurements, anisidine measurement or anisidine value and peroxide. So in this type of test, the Totox value is really takes into account primary oxidation products and secondary oxidation products. So the anisidine will react with unsaturated aldehydes. So aldehydes are secondary metabolites of lipid oxidation. So anisidine will react with unsaturated aldehyde, gives you a color. And then you measure peroxide value, and then the Totox will be a combination of multiplying anisidine value by 2 times the peroxide value. Usually there are charts that would tell you for every type of oil what would be value for fresh oil. Okay, so it is a very common value that is done to measure the current state of lipid oxidation. Now, another very common method, and this is specific for secondary metabolites like hexanal. Hexanal is a common secondary metabolite. It's a volatile. And also like pentane, pentanal, they're all volatile. So oftentimes when we want to determine the extent of lipid oxidation, we get the sample, and it's very easy. We use GC, FID, and it's a headspace method, meaning you don't have to do anything. You don't have to extract any oil or anything. You just put them in um, the vial that is used for the sample, and then you just inject in the headspace. So basically, you wait for it to equilibrate and then take measurement from the headspace. So you're basically injecting a volatile, already a volatilized material, and it goes into the GC, and then with some standards, you would be able to quantify those off flavors that are volatile. And it correlates really well with sensory evaluation. So the higher the hexanol, the worse the flavor is of that product or ingredient. So T-bars is short for thiobarbituric acid reactive substances. If you're taking the advanced food chemistry next semester, that would be one of the labs measuring T-bars. And it is very specific for malonylaldehyde, which is a secondary metabolite of linolenic acid. So it's very specific for linolenic acid. So if you have a food product that is high in linolenic, that would be a good test for measurement. It's very commonly used for lipid oxidation in meat products. So malonylaldehydes reacts with TBA, thiobarbituric acid. It gives you a compound that is a chromophore, and you measure absorption. It correlates really well with sensory evaluation because it's a measure of secondary metabolites. However, malonylaldehyde is very reactive oxidation product, so it might react with other components in your sample, and you get lower absorbance at 530. So most of the time it's an underestimation. But there is a method with HPLC that's very sensitive and is commonly used to determine malonylaldehyde specifically. Okay, the last bit here that I want to talk about is measuring oxidative stability. You know, if you're in food chemistry, I think Fernanda was talking about the kinetics of the reaction and how to determine shelf life. And if we think about determining shelf life, sometimes you have a really long shelf life, and it's very tedious to determine the shelf life using normal condition, normal atmospheric pressure, regular temperature. And so it will take a long time for an experiment to be done. So oftentimes we use something called accelerated shelf life testing. So this accelerated shelf life testing, it allows us to kind of predict by doing several experiments, we can predict the shelf life. But also in lipid oxidation specifically, we use accelerated shelf life to determine something called the induction period or predict the induction period. So the induction period is from time zero, fresh, to how long before we can detect lipid oxidation. So how long the oils remains fresh and oxidized. So that's the induction period. The period until the first sign of lipid oxidation. And this is determining induction period is very useful when we want to determine shelf life of regular oil, or if you want to determine the effectiveness of an antioxidant. Sometimes oils and foods with high fat, they add to it synthetic antioxidant. Sometimes with clean label, they want to add natural antioxidants like carotenoids, for example. So they do experiments to determine how well natural antioxidant, for example, will fare against synthetic antioxidants. So to do that, you get a very fresh oil. You put those antioxidants at different levels, different types in the oil, and then you accelerate the shelf life to determine the differences and which ones will delay the induction period, which antioxidant will have a longer induction period. So the most common test is oven storage test, and we did that for you in the lab for all of your oils, but it was super accelerated. We put the oil at 180 or something, but usually the oven storage test is done at 60 degrees over several days. So that is the official method of doing the oven storage test. For the lab, we just wanted to, accelerate so we can do the experiment in 1 week. But in general, you would store the oil at 60 and then you would take samples over a certain period of time, and then you measure peroxides. You can measure peroxide. Usually it is peroxide in the oven storage method is what you would measure. And then you would plot it and determine at which point you were able to detect the first oxidation product. Okay, so that's one test. It's a very common, good to remember. If I ask you an example in a test or the finding, this would be a good one to remember. There are two others that can be done. One is oil stability index. Usually, if you work in a company, they might have an equipment that does that for you, which is Ransimat. So the principle is you put your sample at high temperature in not water bath, usually on oil bath, because water bath won't get to above 100 degrees C. And then you bubble air through oil to kind of induce oxidation. And then the volatiles, acidic volatiles, will be trapped in another container that has water in it. And so it's basically you would have kind of tubing that links the first flask that has the sample, and then another, you have a stopper with a tube that goes into another flask that has water. And then you would measure the conductivity of the water. And then when you start seeing change in conductivity, that means you have products of oxidation reaching the water and changing the conductivity. And there's an equipment that would do that for you. All right, the last one is an oxygen bomb. It's literally an oxygen bomb. It's literally you get the sample and you put it in pressurized compartment, pressurized with oxygen. And you put that whole compartment at high temperature. And then you monitor a drop in pressure. The drop in pressure is an indication of an uptake of oxygen, because you pressurize this chamber that has your sample in it, closed chamber, with oxygen. And oxygen reacts with the fat. So when fat starts reacting with oxygen, the pressure in the chamber would drop. So when that drops, that would be the induction period for you. All right, questions about all these three methods? All right. Good. Last here is the characterization of the different components in fat. And this is important for nutrition labeling because we need to report total fat, and usually it's done by measuring the fatty acid composition and adding them all up. So measuring fatty acid composition by GC is one that you learned in lab, but we do it with more detail and standards to get every single fatty acid. And then there's also determining mono, di, and triglyceride content done by HPLC, phospholipids by HPLC, cholesterol. You need to, I'll tell you in a minute, cholesterol by GC, and pigments and vitamins by LC as well, by HPLC. And this way we can determine saturated fatty acids, polyunsaturated fatty acid, trans fat, cholesterol, total fat. So all of these methods are used. So we've done the same. And cholesterol is a non-saponifiable matter. So when you saponify the fat, triglycerides will be saponified into glycerol and fatty acid, but cholesterol is not saponifiable. So after saponification, you separate the saponified material from the non-saponified material and would be cholesterol. And then you derivatize with trimethylsilane and you do GCFID, and you can determine cholesterol. This qualitative method in layer chromatography, if you double majoring and you did experimental nutrition, you would see that method. And usually it differentiates if you have phospholipid, it's just a qualitative to see what your sample had. Phospholipids, monoacyl glycerol, diacyl glycerol, free fatty acid, triacyl glycerol. So you put standards on the spots on a thin layer chromatography plate, and then you have your sample and you determine the presence of the different components in that sample to give you an idea of what the composition of the fat in your sample. So, and that's that. We did the lab, and that's it. Any questions about fat characterization? Your favorite topic, isn't it? Nobody cares. Hi, it's a really good topic. All right. Now let's do this next topic. Oh, has this been on the entire time? Nobody said anything. Why are you laughing, Emma? Why are you telling me? Okay. Oh, do you know what the reference is? Or is this thing on? The microphone?
Like
Disney? Is it
Okay.
Disney or Pixar?
Monsters.
Monsters.
Yeah.
Okay. pH and titratable acidity. We're going to remember some concept about your favorite equation in the world, which is Anderson-Hasselbalch equation. Yeah. I thought it was your favorite equation in the world. No. Not it? Okay. Yeah, we're gonna do calculations, so you better put your piece of paper out with your name on it for extra credit. Oh, speaking of extra credit, all right. First of all, I have to ask you 2 questions and I need your honest answer. Raise your hand if you read my email from Wednesday. About this week's lab.
Jog my memory. Yeah, I did. It's been a while.
It's about today, my reminder email.
Yeah, you talked about the protein and fats extra credit.
Okay, raise your hand if you read my email. All right, that's good. I appreciate your honesty. All those that put their hands up. +1, huh? +1. +1. Huh? What's that? I sent it on Wednesday. Friday was a holiday. All right, now another question. Honesty. Who watched the lecture? Oh my gosh, I love it. 1, 2, 3, 4, 5, 6, 7, 8. You watched the lecture? Another +1. Okay, thank you so much for your honesty. Great. If you have not watched the lecture, which is, I understand everybody was happy to go home for a few days. Please do watch. I will ask a question in the final about enzymes. There will be, I guarantee it. So please listen to this lecture. Also, you get a kind of flavor of the teaching of the editor of the book. So it would be good. And then, yes.
harder. Proximate.
No, no, it's characterization. Yeah. Proximate analysis, now that you asked, you've mentioned this, what is proximate analysis?
Just. Your 13 months.
Total carb by calculation.
Okay, yeah.
By calculation only.
Oh.
Yeah. All right. So yes, proximate analysis, we are approximating the major components of food. Yeah, which is moisture, protein, fat, ash, and carbohydrate by difference. Only by difference, not total carbohydrate acid that we did in the lab. Okay. That doesn't count under proximate analysis. All right, very good. Thank you for that question. Where was I going with this? I don't remember. But anyway, let's get started. So, the following is true. You can do this. That's correct. When in doubt, all of the above. So they are organic. Food acids are organic acids. So can you give an example of a food acid or organic in food? Naturally occurring in food? Acetic acid. Naturally occurring in a food? Huh? Citric acid, yes. Ascorbic acid. Vitamin C, malic acid. Lactic acid, very good. There's one more in grapes. The main acid in grapes. Tartaric. Yes. All right, these are the ones that you would hear most about: citric, ascorbic, acetic, lactic, malic, tartaric. Organic acids, very good. They have a good buffering capacity because they are not very strong acids. So what is the acid group usually in these acids? What is the functional group? Carboxyl group. Very good. Thank you. So they all have carboxyl groups, and carboxyls are not strong acids like H2SO4, for example. It easily dissociates, gives the hydrogen very easily, so it doesn't buffer. Quickly dissociate in solution. What else? HCl, quickly dissociate in solution. These are strong acid, nitric acid. So organic acids are usually weak, and the carboxyl group have a higher pKa value than like HCl or H2SO4, strong inorganic acids. All right, and then can they buffer multiple pH? We said yes. How? All right. Think about the chemical structure. Let's say take citric acid. Does anybody by a miracle know how many carboxyl group citric acid has? No. All right, that's fine. I don't expect you to know this. I don't know which course would even tell you this, but okay. Do they talk about acids, aldehydes? No. All right, so it has 3 carboxyl groups. Acetic acid has 1 carboxyl group. When an acid has 3 carboxyl groups, it means it can buffer at 3 different pKa's because every carboxyl group had different dissociation factor. So that's why C is correct. It can buffer at multiple pH, but not all of them. Acetic acid cannot. It buffers at 1 pKa. Okay. Let's think of that one for a minute. True, false? True? True? false. So having the same pH does not mean that you have the same amount of acid. So it takes a lot of citric acid, for example, or acetic acid to lower the pH to a same pH as HCl, for example, because HCl is a very strong acid. It readily dissociates, so it brings down the pH much quicker at a lower concentration than an organic acid. So also, when you have organic acid, they kind of buffer and resist the pH change. Okay, let's give you a relevant example. High protein beverages. Who had high protein fruity beverage before? Nobody? Yeah, you did. Does it taste sour? Fruity, not the milk, not the shakes.
Like a clear one?
Clear.
Yeah.
It tastes a little bit more acidic, sour, astringent. Okay, go drink one after this class so that you know what I'm talking about. Whey protein, whey protein, fruity beverage will be really sour. Why? Because proteins are buffered. To reduce the pH to the typical acidic pH for mild pasteurization, which is usually between 3 to 3.4, you have to dump in a lot of acid. Because every time you put acid, the protein is going to buffer it and the pH doesn't drop. So you keep adding acids to kind of overcome the pKa of the protein. So same pH doesn't mean same concentration. Huh?
Said fruity.
Oh, acidic beverages usually are the fruity one, the sweet one. The neutral are the chocolate flavor, the strawberry flavor would be neutral beverage.
Oh, that's that.
Yeah, protein, water, sugar, stabilizing salts. Yeah. Okay, so it's false. Same pH doesn't mean same titratable acidity, especially if you're comparing two different acids. All right. So there is a difference between titratable acidity and pH. So they're not interchangeable. That's why we measure pH for certain application and we measure total acidity in other applications. So that's why we are differentiating them. And that's what your lab, you're going to be differentiating what pH means versus what titratable acidity is. Titratable acidity is the total amount of acid you actually have, irrespective of your pH. Okay, so this is the total acidity, it's the total concentration of acid. It affects the flavor. Of course, when you dump more acid to reach a particular pH, and it tastes more sour, so it affects the flavor. And also, it is an indicator of maturity. So some fruits, for example, will become less sour with maturity and more sweet. So there is always this indicator of maturity where they measure the ratio of acid to sugar level. pH is measure of free or, what do you call them? Protons. And that means the free hydrogen ions. So, and then when a proton is freed in water, it will form something we call hydronium ion. This is a hydronium. So H plus with water forms the hydronium ion, and that's what decreases the pH actually in this case, decreases the pH. All right. So it measures the active acidity, meaning the dissociated acid. And pH is really a parameter that impacts certain reactions in food. Can you give me what type of reactions pH influences? Yeah, chemical reactions, such as the Maillard reaction. Above 7 would be a good place for Maillard reaction. What else? Enzymatic. Different enzymes require different optimal pH because it impacts their ionization state. Okay. Oxidate, yeah, the chemical reactions basically, but there's one more type. What about microbes? Microbial growth. Okay. All right, so it's a very important parameter for food quality and food safety. All right, so this is the kind of a demonstration between the difference of titratable acidity versus pH. So here, if we have 0.1 normal of HCl and 0.1 normal of citric acid, no, not citric, acetic acid. Acetic acid, one carboxyl group. So same concentration. Look at the difference in pH. So it's 1.2 for a fully dissociated HCl, whereas the acetic acid is 2.89. So very different pH and the same concentration. Because this one is the weak acid and it does not dissociate readily like HCl would. So that kind of illustrates the difference between pH and titratable acidity for two very different acids. All right. So these are common, a few concepts that you want to remember when we talk about acid-base reaction. So acid is a proton donor, so it gives a proton. Base is a proton acceptor. So the proton forms hydronium ion, and the base forms OH minus because it wants to take H plus, so it has a negative charge, and this one gives a proton who has a positive charge. So when the acid loses a proton, it loses a positive charge, and when the base gains a proton, it gains a positive charge or loses a negative. Okay, so when we have acid base, we get salt and water as part of the reaction. So the ion product constant is important for pH measurement. You know, the pH range is from 1 to 14. And now it will tell you, oh, it makes sense because the constant for water at room temperature is 1 times 10 to the negative 14. So the product of the concentration of hydronium ion and the concentration of hydroxyl is the constant, which is 1 times 10 to the negative 14. So that's the range of the pH. Now, let's put this in perspective. pH 7, you have equal concentration of hydronium ion and hydroxyl groups. When you have equal concentration, the pH is neutral. You don't have more acid or more base. The pH is neutral. You have equal concentration of hydronium ions and hydroxyl. So, and the product of that is always 1. So if you have more acid, that means you have less base. If you have more base, you'll have less acid. The product is always 1 times 10 to the negative 14. So that means the pH cannot be less than 1 or more than 14. If that's the range of your pH. So the product is always 1 times 10 to the negative 14. And because of that, knowing this, can you determine 7-Up has a concentration of acid or hydronium ion this much, 3.55 times 10 to the negative 4. What would be the concentration of the hydroxyl? And what would be the pH? pH is negative log concentration of the acid. Okay. There is POH too, which we never worry about, which is the negative log of the hydroxyl group. So we always measure pH, which is the negative log of the hydronium ion. So using this knowledge that you always have the concentration is equal, both of them, 1 times 10 to the negative 4. So if you know one, calculate the other and calculate pH on your piece of paper for your extra credit. There is also a sheet for extra credit pH and titratable acidity in the week of this week. You have until the last day of class to submit all 3 extra credit, each 4 plus 5. So by the last day of lectures, next Wednesday. Anybody? Concentration of OH minus 2.8. Yes. 2.82 times 10 to the negative 11. Very good. Now, what is the pH of 7-Up? Huh? Very good. Okay. So you just apply the equation of the hydroxyl group concentration times the hydronium group concentration equals 1 times 10 to the negative 4. So you do your math, you get the concentration of hydronium ion. Then you use your calculator to get this. You know, I mean, everybody does the calculation differently. This is old style, using old calculator, but as long as you're able to get your calculator to get you that information. Okay. All right, so if a beer has a pH of 4.3, what would be the concentration of hydronium ions? So that whatever you did with your calculator, it will be the opposite. Anybody? pH, I mean concentration? Yes, 5.01 to be specific, if you wish, times 10 to the negative 5. So basically, I do the math, like I said, old school, but your calculator should be able to give you that number. Okay. Is that good? Any questions? You can take a picture of that if you wish. Yeah. All right. So we're going to measure pH of some reagents during or beverages during the lab on Wednesday. So, and you already used the pH meter before, and that would have been the 3rd lab. So you're familiar with the pH meter. Here in this slide, it just tells you what the pH meter is measuring. It measures the free hydrogen, the activity of free hydrogen, and it's basically measuring the change in voltage between a reference electrode and the sample electrode. So that difference in voltage at a very, very small current, infinitesimal current, that difference would be calculated in terms of concentration of hydronium ions and convert it to pH. So the equipment does all that for you. Yeah. Infinitesimal? What did you say?
What is it that difference?
So there is a sample electrode and there's the reference electrode that has a reference solution in it that will always have a constant voltage.
Is that what always?
Yeah, you always have to have your reference. Some new pH meters have the reference and the sample electrode are in one compartment containing. Some old ones will have the reference and the sample electrode. You need to put them both in your sample. So, yeah. So it's basically the reference is like it's the constant voltage that will always be constant at whatever the current is. But then the sample will cause a change in that voltage. So the difference, the change between the reference and the sample is converted to hydronium ion, converted to pH. And the pH meter gives you all of that information. Yeah, so yeah, the old way is when you have them separate. Usually newer electrodes have both of them. And we just need to, take good care of them, make sure they don't dry out. They're placed always in a reference solution. So it's really important to take care of your pH meter. And before you use it, you calibrate. And usually we do 2-point calibration, sometimes 3-point calibration with 3 different pHs, pH 4, pH 7, pH 10. Usually these are the pHs that we use to calibrate using standard reagents. And then we have to clean the electrode. So if we use a solution that has high protein and we're measuring the pH and we keep putting this electrode in solutions high in protein, protein will build up on your electrode. So you need to store it or clean it with enzyme solution to break down the protein and cleanse it. High fat, you really need to cleanse it with alcohol. Other general use, you use acid to clean the electrode. So you just have to keep it maintained, keep it calibrated before you use it, and not let the electrodes dry out. Okay, so unfortunately I have to stop here, but before you go, I just want to let you know I won't be here on Wednesday. I have a medical procedure that was unexpected, but I will be gone for 1 day. So Yi and Gray will lead lab, and Dan Gallagher will give the vitamin lecture. He did that last year, so he's the best. He also teaches vitamins and minerals nutrition course, so he'll be best to teach vitamin analysis. Okay, I will see you Friday. Be good for Yi and Gray in the lab. I'm sure you will be. All right.
Let's stop doing that one more time for me to write down the name again, like full red. Yeah.
From Wednesday. I appreciate your honesty. Okay. Who you got, everybody? And who watched the lecture? Very good. Very good. Thank you.
Answer for the pH of the beer again.
Sorry.
Answer for the pH of the beer.
Page of the beer. Okay, let me stop recording.
Let me see it now. Oh,